Welcome to this explainer. If you're a student gearing up for your embedded systems class and trying to wrap your head around the 8051 microcontroller, well, you are in the exact right place. Today we're tackling Lab 6, and it's all about taming the 8051's timers and counters. These are basically the internal superpowers of your microcontroller. Mastering them, that's what takes you from just, blinking a few LEDs to actually controlling the flow of time and reacting to the physical world. Let's get right into it. Okay, so let's kick things off by defining the absolute most crucial element of your lab. I'm talking about the TMOD register. Think of the 8051 as having two built-in modules, timer 0 and timer 1. But out of the box, they literally have no idea what they're supposed to do. The TMOD register is essentially the ultimate control panel for your microcontroller. By writing specific values to TMOD, you're instructing these modules to act as either internal stopwatches to measure time delays, or as external event counters to tally up things happening outside the chip. It all starts right here. Here's our game plan for today. We'll start by setting up the simulation, then move on to generating short time delays, mastering long time delays, and finally, counting external events.
Part 1. Setting up the simulation. This is where we build out our hardware and software sandbox.
So before you write a single line of code, you need to get your virtual hardware ready. When you're setting up your project in Proteus, this is the exact schematic you're going to want to draw. Pay really close attention to your central chip here, the AT9C52, which is our 8051 variant. Notice the connections carefully. You're going to hook up an array of 8 LEDs to port 2. That's going to be your primary visual output. You've also got physical buttons connected to port 1 and port 3. Honestly, taking the time to wire this virtual circuit correctly is absolutely the foundation for everything else we're doing today.
Moving over to the software side, you'll want to follow these 3 rapid-fire steps in your Keil IDE to make sure your compiled code can actually talk to your Proteus hardware. Step 1, just create that new 8051 project. Step 2, and this is a huge one, ensure you select an Intel 8051 microcontroller that supports C programming, specifically the 89C52 series, so it matches your schematic perfectly. And step 3, dive into your target options and enable hex generation. That hex file is absolutely crucial. Think of it as the brain transplant you'll eventually load into the Proteus chip to bring your whole simulation to life. Part 2. Generating short time delays. Let's teach the 8051 how to keep a steady beat. Now here's the thing, when you're generating a really high-speed signal, LEDs that blink too fast are just going to look like a solid light to the human eye. So to actually prove our code is working, we need some special equipment. Make sure you grab the virtual oscilloscope from the Proteus debug toolbar. I swear, this menu is like the Bermuda Triangle for engineering students. Everyone always loses it. It's right here under Virtual Instruments, and then Oscilloscope. You'll connect this to your output pin so we can visually measure the otherwise invisible time delays we're about to program. And this just beautifully illustrates the connection between your software and your hardware. On the left side, we've got our assembly code. By setting TMOD to 01, we configure timer 0. We load our starting values into the timer registers, and then we just repeatedly call a delay subroutine to toggle pin 3.0. Notice how the assembly code directly generates that perfectly symmetrical 50% duty cycle square wave on the oscilloscope on the right. The timer ticks up, overflows, toggles the pin, and repeats. It is literally incredibly precise. Part 3, mastering long time delays. Let's talk about pushing past the timer's maximum capacity. So what do we actually do when an 8051 timer maxes out? Remember, an 8051 timer is only 16 bits, meaning it hits its absolute limit pretty quickly. We solve this hardware limitation strictly through software by using nested loops. Take a look at this assembly code, which adapts example 13 from your textbook. Instead of just running the timer once and toggling a pin, we run the timer, let it overflow, and then decrement an entirely separate register. Only when that separate register hits 0 do we finally toggle our LED. This clever trick allows us to multiply the base timer delay to create massive, highly accurate wait times. Let's break down how this builds mathematically. First, TMOD is set to hex 10, which configures timer 1. Then, we take register R3 and load it with the decimal number 200. Basically, R3 is our multiplier. We start the timer, and when it overflows, we hit the DJNZ instruction. That stands for decrement and jump if not 0. This instruction decreases R3 by exactly 1. If R3 isn't 0 yet, it forces the timer to run all over again. By making the 8051 run a maximum timer loop 200 consecutive times, the result is a wait of roughly 14 seconds before port P2.0's LED finally blinks. Now, 14 seconds might not sound like a long time to us, but to an 8051 executing millions of instructions per second, you've just forced it to wait an absolute eternity before blinking that LED.
Part 4. Counting external events. Now we're looking outside the microcontroller. We've spent this entire time looking inward, measuring the 8051's internal clock. Now we're going to teach it to look at the outside world. Think of the distinction kind of like this. In timer mode, the 8051 acts like a stopwatch. It strictly counts the steady internal clock pulses generated by its own crystal oscillator to measure elapsed time. But in counter mode, it becomes a turnstile. It completely ignores its internal clock and instead monitors a specific external pin, just waiting for a physical action, like a sensor triggering or a user pressing a physical button.
Now see how the code perfectly aligns with this concept? In the first line of the assembly, TMOD is loaded with the binary value 0110000B. Setting that specific bit configures timer 1 to operate as an external counter. We then set pin 3.5 to act as an input. Once we start the counter, the 8051 is constantly monitoring pin 3.5. Every single time you press that physical button in your Proteus schematic, the counter increments, and we move that new value directly to port 2. As you click the button, the red LEDs on port 2 instantly reflect the new count in binary format. It's literally reacting to you in real time.
And just like that, you've conquered Lab 6. Armed with this knowledge, you are not just passing an assignment, you now have the foundational skills to engineer complex, real-world systems. You can measure perfect time intervals, and you can digitally count external physical events. Whether it's a digital clock, a conveyor belt counter, or an engine RPM monitor, these are the exact same mechanics running under the hood. So now that your 8051 has these superpowers, what real-world embedded system are you gonna build next? Thanks for joining me for this explainer, and good luck in the lab.